Imagine, you are constructing this massive state-of-the-art skyscraper. You lay down this beautiful, intricate foundation right in the lobby.
Right, a really solid base.
Exactly. But there is a massive catch to how this specific building works.
Mm.
Every time you add a new floor, the physical weight doesn't just, rest on the steel frame.
Oh, it actively compresses the floor directly below it.
Yeah, it just crushes it.
Yeah.
So by the time you're building the 50th floor, the ceiling in the lobby is basically touching the floor. The space is totally crushed.
And the people working at the very top of the building have absolutely no idea what that original foundation even looked like.
Right. And we're pulling from a fascinating new technical report today by the Kimi team. It's titled Attention Residuals, and we're also bringing in some context from the Generative Foundation.
Because it turns out this whole architectural nightmare you just described, that is exactly what is happening inside the brains of our most advanced AI.
It's crazy to think about. But today, for you listening, we are going to unpack this fundamental flaw in how current large language models, or LLMs, are built.
And more importantly, we're going to explore the solution.
Yes, this brilliant, really elegant solution that is actively shifting the entire landscape of AI architecture. We're going to try and make the math intuitive so you can understand exactly why this next generation of AI will be vastly superior at complex reasoning.
It really is a massive leap forward.
Okay, let's unpack this. So this skyscraper is basically collapsing under its own weight. But, why can't AI developers just reinforce the foundation? What is physically happening to the data down in that lobby?
Well, to understand the collapse, we really have to look at the invisible bottleneck holding everything back. And that is the standard residual connection.
The residual connection.
Yeah. In the world of deep neural networks, this is essentially the fundamental pathway that passes information from one layer of the AI to the next.
Like handing off a baton.
Exactly. But in current LLMs, information travels through these layers using a very simple, almost rigid formula. The new state of information is simply the old state plus whatever transformation the current layer just performed.
So it's literally just addition.
It is a uniform additive accumulation. Every single layer just piles its work directly on top of the previous layer's work.
So it's basically just a running tally, right?
Mm-hmm.
Layer 2 takes layer 1's output, does some math, and simply adds its new result to the pile.
That is the core of it, yeah. But the problem really arises when you combine this simple addition with a technique called pre-norm.
Pre-norm. Okay, what does that do?
Well, neural networks deal with massive complex numbers. If you just keep adding and multiplying layer after layer, those numbers can completely spiral out of control and, destabilize the training process.
Oh, so the math just gets too big to compute.
Right. So engineers apply pre-norm, which basically normalizes the data. It wanes the numbers back into a predictable range before the layer performs its specific transformation.
That sounds like a good thing, though. You're keeping the math stable.
It is entirely essential for training, but, and here's the catch, it creates this nasty side effect known as pre-norm dilution.
Pre-norm dilution.
Yeah, because you are normalizing the data before the transformation, but then continually adding these new transformations to that running tally we talked about. The sheer volume of the accumulated data just grows.
Oh, exactly.
Mathematically, the magnitude of the hidden states grows linearly with depth. We express that as O of L, where L is the number of layers.
Wait, so O of L basically means the deeper the model, the bigger the pile.
Exactly. The data just gets physically larger and, frankly, louder the deeper you go into the network.
So by the time you hit, say, layer 80, the new information being generated by that specific layer is basically competing with the accumulated noise of 79 previous layers.
And because of that volume, the original input gets totally lost. The crucial data from the early layers, like the actual prompt you typed into the AI, gets entirely drowned out. Yeah, the deeper layers are practically shouting over this accumulated noise just to stay relevant. The research actually shows something crazy.
What's that?
A significant fraction of layers in modern AI can be pruned away completely with minimal loss to performance.
Wait, really? You can just delete layers?
You can, simply because they aren't effectively contributing anymore. They're just entirely lost in the noise of the running tally.
It makes me think of a giant corporate email chain.
Oh, that's a good way to look at it.
You know the ones, right? Where every time someone replies, they just forward the entire massive thread.
Yes, the dreaded reply all.
Exactly. By the time you get to reply number 50, the original crucial message, the whole reason the email chain even started is buried under 49, sounds good to me, replies.
Right.
If you need to selectively find that original point, you just can't. You were just looking at a huge wall of text.
That is a highly accurate way to visualize the breakdown. You literally cannot selectively retrieve the original context. And what's fascinating here is the time versus depth duality.
The time versus depth duality.
Yeah. This email chain depth problem we're seeing in modern transformers. It's the exact same problem that older AI models, like recurrent neural networks, used to have over time, or sequence-line.
Oh, right. Older models used to just forget the beginning of a paragraph by the time they reached the end of it.
Exactly. They suffered from sequential amnesia because they compressed all past sequence information into a single, overloaded, hidden state.
Right. They couldn't look back.
The transformer architecture fixed that problem across time by introducing the attention mechanism that allowed the model to selectively look back at any previous word in the sequence.
Okay, so they fixed the time problem.
They did, but while developers fixed the problem across time, they accidentally preserved the exact same problem across depth.
So for you listening, I mean, imagine trying to solve a complex, multi-step math problem, but being forced by the laws of physics to completely forget your first step by the time you reach the fifth step.
You would fail every time.
Exactly. You would totally fail. And this is exactly why current AI sometimes just completely loses the plot on complex reasoning tasks. It literally loses your original premise in its own internal noise.
Right.
So, if the corporate email chain approach is failing across depth, how do we fix the replies?
Well, we apply the exact same solution that worked for sequences.
Yeah.
We bring the concept of attention to depth.
Okay.
This is where the Kimi team's Attention Residuals, or AttnRes, comes in. Instead of that rigid additive accumulation, which is just blind addition, AttnRes uses a learned input-dependent softmax attention mechanism over the preceding layer outputs.
Wait, softmax is a term that gets thrown around a lot in AI, but in this specific context, what does it actually do to the data?
Think of softmax as a function that forces the AI to be strictly picky with its resources. It gives the layer a strict budget of 100% attention.
Okay, a strict budget.
Right. So if the current layer decides it absolutely needs to give 90% of its attention budget to layer 2, it only has 10% left to distribute among all the other layers. It completely transforms the system from a rigid linear structure, just adding things up endlessly, to a flexible mechanism where probabilities are distributed based on what is actually needed.
So it gets to say, I need heavily from layer 2, a tiny bit from layer 5, and absolutely nothing from layer 8.
Precisely.
But how does a layer actually execute that search? I mean, structurally.
The mechanism is wonderfully lightweight, actually. Each layer is given one single learned pseudo-query vector.
A pseudo-query vector.
Yeah. You can think of it as a dedicated search query of a specific dimensional size, which we call D. This allows the current layer to look back at all previous layer outputs and assign an attention weight to them.
And what stops the loud layers from just dominating that search?
Good question. To prevent those naturally louder layers from dominating the selection process, they apply RMS norm, which normalizes the previous outputs so that the attention weights remain perfectly balanced.
Wait, let me make sure I'm following this because it sounds a bit chaotic. If every single layer gets to look back at every previous layer, how does it know what to look for? If this search query is pseudo and completely decoupled from the actual word the AI is currently processing, isn't it just searching blind?
It seems counterintuitive at first glance, I know. You would naturally assume the query should be built based on the specific word, the input that the layer is currently looking at.
Right, that would make sense.
But the key here is that this pseudo-query is learned and then fixed during the training phase. It acts as a permanent structural anchor.
Oh.
The researchers actually ran an ablation study, which is where you remove or alter parts of a model just to see what breaks. They tested an input-dependent query, and they found a massive flaw.
Really? What broke when the AI had to look at the word first to build a search query?
It introduces severe sequential memory bottlenecks during the decoding phase.
How so?
Remember, when an AI generates an answer for you, it decodes and generates those words autoregressively, meaning one by one. If a layer has to wait to see the newly generated word before it can even build its search query to look back at previous layers, the whole system just stutters. The computational wait time piles up.
Oh, because it's waiting in line to build the query every single time.
Exactly. By making the query decoupled and learned over time, it becomes a permanent, highly optimized routing instruction. The layer instantly knows where to look without waiting, making it both highly effective and computationally much cheaper.
Okay, so full attention residuals sound like a massive upgrade in theory. The layers can look back, find exactly what they need, ignore the loud noise, and do it without stuttering.
Yes.
But, I mean, if this is so perfect, why isn't it just deployed in every single model right now?
Because theory often hits a brick wall in real-world engineering, specifically regarding communication overhead.
Hardware limits.
Always. When you are training massive AI models, they physically do not fit on a single computer chip. You have to chop the model's brain up and distribute it across multiple GPUs in a process called pipeline parallelism.
So like layers 1 through 10 live on GPU A, and layers 11 through 20 live on GPU B.
Exactly.
Oh, I see where this is going. If every single layer has to selectively look back at every previous layer's output, doesn't the data traffic between those separate chips just explode?
It creates a catastrophic communication bottleneck.
Yeah.
Mathematically, it is an O of L times D bottleneck.
Yikes.
Yeah. GPU B would have to constantly ask GPU A to send over the massive full-resolution outputs of every single early layer. The hardware would spend all its time just transmitting old data across cables instead of actually calculating new thoughts.
You would choke the hardware entirely.
Completely choke it.
So how do we get the benefits of this selective memory without, melting the GPUs?
Well, the researchers engineered a highly practical fix called Block AttnRes.
Block AttnRes, okay.
Right. Instead of forcing every layer to look back at every single past layer individually, they partition the layers into blocks. Let's say n blocks. A typical setup might group them into 8 blocks.
Okay, making chunks.
The network then squashes an entire block of previous layers into a single summary representation. So now, a layer only attends to those n block-level summaries, plus the detailed partial sum of its own current block.
Here's where it gets really interesting, because I love this concept.
It's very clever.
It is exactly like reading the executive summaries of the first 7 chapters of a dense textbook, but reading every single word of the current chapter you are actively studying.
That is a brilliant analogy.
Right, you get the broad context of everything that came before without having to hold the entire massive book in your working memory all at once.
Exactly.
But I do have to ask, if I am only reading the summary of Chapter 2, what if there was a tiny, crucial mathematical detail in there that I absolutely need for Chapter 8? Doesn't squashing the layers into a summary destroy the fine details?
You'd think so, but that is the beauty of neural network training. The network actually learns how to construct those block summaries to preserve the most critical tokens, knowing they will be needed later.
It plans ahead.
Basically, yes. We will touch on how it does that in a moment. But mathematically, this block approach drops the memory and communication overhead down from O of L times D to O of N times D.
Oh, wow.
Since N, the number of blocks, is a fixed small number, the data traffic stops spiraling out of control.
I know you always appreciate the infrastructure side of these papers. How did they actually optimize the hardware to make this run smoothly in practice?
Oh, I love this part. The system optimizations they built to support this are incredibly elegant. For the training phase, they implemented cross-stage caching.
Catching the summaries.
Yes. Since those block summaries don't change once they're computed by the early GPUs, the later GPUs just cache them locally in their own memory instead of constantly asking for them to be retransmitted. It entirely eliminates redundant data transfers.
That's incredibly smart. And what about during inference? When the listener is actually sitting at their computer asking the AI to generate a response.
For inference, they use a clever two-phase computation strategy.
How does that work?
The system bashes all the interblock queries together in one massive parallel calculation to get the broad context. Then it sequentially processes the interblock lookbacks for the fine details.
Wow.
Furthermore, they use something called sequence sharded prefilling, which distributes the memory load of the sequence across the devices. The results are just staggering.
Give me the numbers.
If you give the AI a massive 128,000 token prompt like dropping an entire novel into the chat box, the memory overhead drops from 15 gigabytes to roughly 1.9 gigabytes per device.
That is a massive reduction.
It becomes a drop-in replacement for standard models with less than a 2% inference latency overhead.
Okay, so we have a beautiful theory-bringing sequence, attention to depth. And we have the engineering mechanics like Block AttnRes and caching to make it actually run efficiently on physical hardware.
We do.
But does it actually make the AI smarter?
Well, the proof is in the scaling laws. The researchers found that Block AttnRes matches the loss. which is basically the primary metric for measuring an AI's error rate of a baseline model that was trained with 1.25 times more compute.
Wait. So just by changing how the layers route information to each other, it performs like a model that costs 25% more money, time, and electricity to train.
Yes, it punches significantly above its compute weight class. And that pre-norm dilution problem we talked about at the very beginning.
The crushing weight of the lobby.
Exactly, it is completely solved. Because the model is selectively attending rather than blindly accumulating, the output magnitudes remain bounded in a healthy periodic pattern across depth.
They don't spiral into infinity anymore.
They don't. Consequently, the gradient distribution, which is how the model updates its weights and learns from its mistakes, becomes much more uniform across all layers.
And they didn't just test this in a vacuum either, right? They integrated this architecture into the Kini linear model.
Yes, which is a massive 48 billion parameter model, and they pre-trained it on 1.4 trillion tokens.
A true real-world scale deployment.
Absolutely. And the benchmark jumps were incredible, specifically in compositional complex tasks.
Like what?
Well, GPQA Diamond, which is a notoriously difficult graduate-level reasoning benchmark that trips up most models, jumped by a positive 7.5 points.
That's huge for that benchmark.
It is. Minerva Math went up by 3.6 points. Human Evil, which tests logical coding ability, improved by 3.1 points.
So what does this actually mean for the listener? I mean, if I am using an AI to help me code a complex database structure or, solve a really tough logic problem for a work presentation, how does this architectural shift change my day-to-day experience?
If we connect this to the bigger picture, tasks that require multi-step reasoning benefit the most.
Right.
When you give an AI a complex coding prompt, it requires a long chain of logic. Under the old system, by step 10, the AI might completely forget the specific variable constraint you mentioned in step 1.
Because it got buried in the email chain.
Exactly. But with AttnRes, because later layers can selectively retrieve earlier representations, the AI can actually remember the exact premise of your prompt by the time it reaches its final output layers.
So it doesn't lose the plot halfway through writing the code.
It doesn't. The logic remains totally sound. There is also a really fascinating factual addition from their optimal architecture sweep.
Ooh, what did they find?
They tested different shapes of LLMs to see what dimensions worked best with AttnRes. It turns out this mechanism actually shifts the ideal LLM design to be deeper and narrower than current standard transformers.
Narrower but deeper.
Because the layers can finally communicate effectively across vast distances without drowning in noise, the model can exploit depth much more efficiently.
That makes perfect structural sense. If adding floors to the building no longer crushes the lobby, you can finally build significantly taller skyscrapers.
And taller skyscrapers allow for much more complex processing.
Now, the benchmark numbers going up is fantastic. But to truly understand the mechanics of this, we need to look inside the black box.
Yes, we do.
We need to see how the layers are actually utilizing this new superpower of selective memory. When the researchers visualized the learned attention weights, what did they actually see the AI doing?
They analyzed the attention patterns of a 16-head model to see exactly where the layers were focusing their search queries, and they found 3 highly distinct patterns.
Okay, what was the first one?
First, preserved locality. Layers still rely heavily on their immediate predecessor, so layer 5 looks mostly at layer 4.
Which is completely logical. You build your current thought off the immediately preceding thought.
Right, sequential. But the second finding was the emergence of learned skip connections.
Skip connections.
Yeah. Layers very deep in the network, like layers 15 and 16, would suddenly reach all the way back to the early blocks. They were purposefully skipping over the middle layers to grab context directly from the beginning of the process.
It is incredibly similar to human thought patterns.
How so?
Think about when you are writing the final conclusion to a complex 10-page essay. You're deep in the network, right?
Yeah, page 10.
You mostly look at the paragraph you just wrote to ensure the flow makes sense. That is the preserved locality.
Right.
But simultaneously, you glance all the way back to page 1, to your opening thesis statement, just to make sure your conclusion actually answers your original premise.
You are anchoring your final output to your original input.
Exactly.
And that brings us perfectly to the third finding, the embedding persistence. The researchers noticed that the very first token embedding, that raw initial thesis statement from the user, stays highly relevant throughout the entire depth of the network.
Wow, even at the very end.
Especially for pre-attention layers, the model constantly keeps one eye firmly fixed on your original prompt.
That answers my earlier question about the textbook summaries. I was wondering, even when using the Block AttnRes executive summaries, does it still manage to keep that original thesis statement alive?
It does. Block AttnRes preserves this exact same structural pattern. The diagonal dominance, meaning looking at the immediate past, and the layer specialization remain completely intact, even when you compress the history into blocks.
That's amazing that it doesn't lose that detail.
In fact, squashing the data into block summaries actually acts as an implicit regularization.
Meaning it keeps things tidy.
Exactly. By forcing the model to rely on summaries, it keeps the neural pathways clean and decisive. It actively prevents the model from overthinking the noise of the middle layers.
Okay, to bring all this together, by simply replacing a rigid addition symbol with a selective, learned attention mechanism over depth, AI models can completely overcome the echo chamber of pre-norm dilution.
Correct.
They can punch 25% above their compute weight class, and they become drastically better at complex multi-step reasoning because they literally never lose sight of the foundation.
It represents a fundamental structural shift from rigid accumulation to dynamic, intelligent retrieval.
I want to thank you for joining us on this deep dive. It is so easy to just look at the text output of an AI on a screen and take it for granted. But it is vital to understand that the tools you use every day are evolving at a structural, microscopic level to better serve your workflows.
The architecture of artificial thought is truly being rewritten from the ground up.
It is.
This raises an important question for the future, though.
No.
The researchers noted that this sequence-depth duality means we've just successfully brought time-based attention to depth. But what if we take that logic a step further?
What do you mean?
If depth is now as flexible and dynamically searchable as sequence length, could future models dynamically choose how deep they need to be?
Wait, choose how deep to be.
Well, currently, an LLM runs through a fixed number of layers for every single query, regardless of difficulty.
Right, it's a fixed building.
But what if the AI decides to run through 200 layers of depth for a highly complex physics question you ask it, routing back and forth to double-check its math, but only utilizes 5 layers of depth for simple hello? Could the concept of an AI thinking longer soon mean adapting its architectural depth on the fly?
So no more fixed blueprints. Just a building that constructs its own floors perfectly to whatever height the specific problem requires at that exact moment.
Exactly.
That is definitely something to ponder as we look toward a fascinating future of dynamically scaling AI brains.